Hello everyone. Hi, I'm Orkumata Dash, and in this video, I'm going to discuss the fifth problem that came in CMI 2023 this year. So the exam was held last week, so the official solutions are not out yet. Most of the students have failed in most of the parts, even in this problem five. So everyone wanted to know the full solution, how we can approach. For this, I mean, the students who have only learned calculus, they might face some problem going through the solution. But yeah, those who have learned real analysis, so it won't. They must know the terminology and they can approach the solution. Without wasting time, let's start. And I hope I'll be able to give a nice solution which you can admire. So yeah, first let's discuss the problem. So the problem is saying that, so this is CMI 2023, B5, the second last problem. And yeah, so it's given that all the functions that have been considered are differentiable. So that means, and they are real valued functions. So they are from R to R, so real to real. And F compose F denotes the composition of F twice. Okay, so these are the given things. And now there is the first part of the problem is saying that if f of f of x is equal to f of x for all x belongs to R, then for all x, f dash x is equals to, or f dash f of x is equals to, fill in the blanks and justify. Okay, so this was the easiest part. Almost everyone, I think, did this. The second part says that we have to assume that the range of f is one of these forms, that is from minus infinity to infinity, or closed a to infinity, or negative infinity to b closed, and closed and bounded ab. Now, so this is, we have to assume, so this was given basically to assume that the function is not constant. And then we have to, so there is a condition that show that if I double compose f, then if it's equal to f, then the range of f is R. So that means the range is whole of the real numbers. Okay, and there is a hint to it, that is, consider a maximal element in the range of f. So consider a maximal element in the range of f. Okay, so what's the idea? Like, if I consider a maximal element in the range of f, so basically the idea is to show that maximal element is not finite. Okay, and similarly we can get a hold of minimal elements just similarly and show that it's not finite. And so first showing that the range is whole of R. Okay, so that's the idea. And now coming to part, so that was part 2, and now coming to the part 3, which was the most important one, that is, if G satisfies, that is, G compose G is equals to G. So if I'm composing G thrice, so again I'm getting back G, then G is on to. Now prove that either G is strictly increasing or strictly decreasing. Okay. And further, we have to show that if G is increasing, then G is unique. So again, if you haven't tried out the problem, so please do try it out. Pause the video, try it out, and then look at the solution. Okay. So let's proceed to the solution. Again, the very first part, there is nothing. We have f of x is equals to f of x, and so since f is given to be differentiable, so we differentiate this f of x f dash x is equals to f dash x. Now you take everything on one side, take common f dash x, so you get that either f dash x is 0 or f of x is equals to 1. Okay, so f dash x is equals to 0 or f dash f of x is equals to 1. First part is done. Let's go to the second part. So second part is saying us that consider that the function is not constant, and double compose of f is f. Then we have to show that the range of f is the whole of R. So going to the second part, that is, yeah, and also we'll use the hint. Okay, so now we prove that if f is not constant, then because it's given that the range is all those, so the range is, looking at the range, we can easily say that f is not constant. Okay, so then we claim that f of x is equals to x. So this is the main part. Okay, and in particular we are trying to prove that if f is the range of f is whole of R. Okay, so yes, now again we'll use the hint. So we'll consider suppose alpha, which is suppose infimum of f of R, and beta to be, suppose let's take it to be supremum of f of R. So f of R is basically the range. So in the range I'm taking considering that alpha is the infimum and beta is the supremum. Okay, now since it's given that f is differentiable, so f is continuous and f is not constant, right? So then what we can have is we can have, or we have basically, then we have alpha is strictly less than beta, and alpha comma beta, this interval is a subset of the range f of R. So now if we are like if we take now it was said that our function is going from R to R, so the domain is whole of R. So this alpha beta, this interval, so that's also is an R, right? So if we are considering any particular arbitrary x a point, if x belongs to open alpha beta, this interval, then we can say that x is equals to f of t for some t, because this is nothing but just the intermediate value property. Okay, and now let's I mean, we know that double compose, when we double compose f, it gets back to f. So let's double compose this on both the sides. So like f of x we are getting, then it's equal to f of t. and f of t would be nothing but f of t, because double compose is nothing but again back to f, and f of t as our as we have considered, it's equal to x. So we are basically getting that for x belonging to this open alpha beta in this interval. So for all such x, since x was arbitrary, any point, so we have proved that f of x is equals to x. But note that we still haven't proved for all x in R. Okay, that is still left. So only this much we have been able to prove, that in this particular interval f of x is equals to x. Okay. Now what now we'll work with this alpha and beta. Okay, so let's first consider that, let us assume that beta is finite. Okay, so then by continuity of f, we can say that f of beta will be equals to beta. Okay, since beta is finite, and in that interval we are having for all x, f of x is equals to x, and so by sequential criteria I can easily say that since f is continuous, so we'll get f of beta is equals to beta. Okay, so now f is also differentiable at beta, and hence we have f dash beta to be limit delta tends to 0 plus f of beta minus delta minus f of beta minus delta, and that would be equals to limit delta tends to 0 plus. So since I am approaching from the left hand side, so this will be nothing but, I have already proved that f of x is equals to x. So beta minus delta minus beta and divided by minus delta. So which is basically 1. Okay. And now let's approach from the right hand side. So limit delta tends to 0 plus f of beta plus delta minus f of beta by delta will be nothing but f, it will be equals to f dash beta, because at beta we are considering beta to be a finite value. Okay, so at beta the function is differentiable, so this should be equals to f dash beta, and which should be equals to 1. Okay, now since this is equals to 1 and delta is positive, so for small enough delta obviously greater than 0, we will have that f of beta plus delta will be greater than f of beta, and f of beta is equals to beta. So we are basically getting that our hypothesis was saying that beta, the supremum, we considered the supremum here. So beta was the supremum of the set, the range set. So finally, we are proving that there is a point where at beta plus delta, f is taking value greater than beta, and that's a contradiction here. So it's a contradiction here, and thus what we considered was beta was finite, so beta will be now infinite. Okay, and just similarly, so this is don't consider this as like something equal. So infinity is just a concept. Okay, so these are some notations that we usually use. Okay, it doesn't literally mean equal. Okay, and yes, so similarly, assume that Again, now we'll work with alpha. So it's just basically the same thing. That is, alpha is greater than negative infinity. So again, I'm considering that alpha is something finite. Okay. And now again, by continuity of f, we have f of alpha is equals to alpha, and f is differentiable at alpha. So again, just the same logic, the same approach. F dash alpha is limit delta tends to 0 plus. So you can just you can leave it if you don't have time to show that. You can just leave it by writing that similarly. But if you have time, just show it, because a little change is there, but almost the same. So delta change tends to 0 plus. So which is basically alpha plus delta minus alpha by delta, and that is equals to 1. But then what we have is limit delta tends to 0 plus f of alpha minus delta minus f of alpha. So this is the little change here. So here now we are for this, that is f of so delta is now tending towards here, that is 0 plus, and we are having that this is f dash alpha, and this should be equals to 1. Now again, for small enough delta greater than 0, like for small enough, okay, so very small, however small it might be, but there should be, okay, because this is happening, okay, and there will be getting that f of alpha minus delta would be less than f of alpha, which is nothing but equals to alpha. And again, this is a contradiction, because I'm getting I considered alpha as the infimum of the range set, but here we are getting that at certain point it's taking value lesser than that. So, and that's a contradiction, and so that proves that alpha is basically it's not finite and going till negative infinity. Okay, so again, so that means like we have proved basically, that is here, that is f of r is equals to r. Okay, so you have to know these notations, like f of r is equals to r. So what does it actually mean? So that means the range of f is the whole of r. Okay, so and we have also proved that yeah, so f of x is equals to x, because since alpha and beta are not finite, so like alpha and it's the then since this x that I took was between alpha and beta, so and x was arbitrary, so now this interval is nothing but from negative infinity to positive infinity, and so that's why, like, for uh, every x it's working, that is f of x is equals to x. Okay, and thus we have proved not only that the whole the range of f is the whole of r, we have also proved something greater, that is f of x is equals to x for all x in r. Okay, so this part is done. Now going to the third part, which says that again we have our function g, which we are composing it thrice, then g is onto, then we have to prove that either g is strictly increasing or strictly decreasing. If g is increasing, then g is unique. Okay, so let's come to that part later. So first, composing g thrice, we have to show that we get back g, then we have to show that g is onto, and also we have to show that g is strictly increasing or strictly decreasing. So yeah, so for this part, again, g is from r to r. G is a real valued function, is differentiable. Okay, and it's not constant, and satisfies G compose G is equals to G. Now let's consider the function f as G compose G. Okay, so this is let f be a function which is nothing but G compose G. Okay, so now what we are going to get is, that is, f compose G will be equals to G, because G compose G is equals to G, and that's what we are getting here. And since G is not constant, so that implies f is not constant as well. Okay, so here this is the f that we are considering. Don't mix it up with the previous f in the second part. Now let's get some beautiful properties. So f compose f is nothing but f compose G compose G. F is nothing but G compose G, and which is nothing but G compose G, because f compose G is equals to G. Okay, and so this is again equals to f by our definition of G compose G equals f. So what we are getting is f compose f is equals to f. So we are back to the second part. So that means again we are getting a function f which is basically satisfying the given condition in the second part. Okay, and thus we can use the second part. So that means now by part 2 we can say that f of x is equals to g of x, that will be equal to x. And now let's differentiate this equation with respect to x. So we get g dash g of x g dash x is equals to 1. Okay, so this is an important result that we got. Now the main part lies. Okay, so here the next part is a little difficult to think and go about in the exam hall, but yeah, let's go. So now we'll assume that, now you see that since I have to show that my function is strictly increasing or strictly decreasing, so all I have to prove that like my g can so if I can prove that my g like cannot be something like somewhere it's increasing, somewhere it's decreasing, so then we can come to such a conclusion. So let's see. So we'll assume that there exists x1 x2 such that g dash x1 is greater than 0 and g dash x2 is less than 0. Okay, so now consider the case that is consider x1 is less than x2 without loss of derivative. We can take that one of them is bigger than the other. So then there exists points y1 y2 such that x1 is less than y1 less than y2 less than x2 such that g of y1 is greater than g of x1. Okay, because g dash x1 is greater than 0, so there exists such points y1 and y2, so that and also g of y2 will be greater than g of x2. Okay, and now if we look at, that is if we look at the segment closed and bounded x1, x2. So since this is a closed and bounded set, it's a compact set. So a continuous function will achieve its maximum as well as minimum at some point. And so the maximum of G on the segment x1, x2 closed and bounded is achieved at some point t belonging to x1 comma x2. Okay, but then what we have is, so that would imply that G dash t will be equals to 0, and which is not possible because that would contradict this result. Okay, so that means it's not possible that we can have such points where such that is the increasing and the decreasing part will happen. Okay, and similarly, consider the case where x1 is greater than x2. So here we considered x1 is less than x2. So consider x1 is greater than x2. Again, then there are points y1 or y2 such that x2 would be less than y2, less than y1, less than x1, such that, so there exists y1, y2, such that this is happening, and such that g of y2 is less than g of x2, and g of y1 is less than g of x1. And now again, the minimum of g on the segment x1, sorry, x2 comma x1, x2 comma x1 is achieved at some point t belonging to x1 comma x2, and again that would imply that g dash t is equals to 0, and that is impossible. Okay, so that means what we are getting is that g dash x is, so either g dash x is strictly greater than 0 for all x, and g is strictly increasing, or g dash x is less than 0 for all x in R basically, and g is strictly decreasing. Okay, now the last part where we have to assume that g is strictly increasing and we have to prove that g is unique. So assume that g is strictly increasing. So okay, now if g of x is greater than x, then x is equals to g of x, which is basically greater than g of x, which is greater than x. And again, that's a contradiction. X is greater than x. Similarly, if g of x is less than x, then x is equals to g of x, which is less than g of x, is less than x, and again which is impossible. And so g of x is equal to x. And thus the final conclusion, that is g is unique. Okay, and hence proved. So I hope you like the solution. So yeah, so these are I mean some of the lengthy solutions, like CMI problems are a little more difficult problems. Like we have every year such lengthy solutions to some of the CMI problems, subjective problems. So nothing we can do, but yeah. So yeah, so B5 and B6 are solved and posted. So I'll post the other solutions as soon as possible. So I hope you like the solution. So please don't forget to like the video, and please do subscribe, and thanks for watching, and keep watching and keep learning, and see you in the next one.